Martin Zeman. Title of the lecture is A Panoramic View of Inner Model Theory for Not So Small and Large.
Yeah, thank you. And I would like to thank the organizers and the program committee for inviting me. And also I would like to thank Menachem Magidor for suggesting this great title. So I guess this is late in the day, so this will be an easy talk, and I will go very slowly, and I will start from very, very bottom and work a little bit upwards. And really what I would like to do in those 4 lectures is somehow to give you some idea how this inner model theory, which goes from L up to several Boolean cardinals, how that works. And so I will do some things in kind of a detail, but at the beginning I will spend some time with 0 sharp, although probably many of you know 0 sharp, but when I looked at the list of participants, and there was a large number of people who are not really, who at least who wrote they were not, my feeling was they didn't have that much touch with inner model theory. But what I really want to do, I would like to present 0 sharp as a mouse and show you how to do certain things which we later do in inner model theory. So I will go slowly here, and then I will introduce an extender model, and then we just translate everything into real inner models without going that much into details. Yeah. So let me start with a baby version and a little bit of history. So that's year 1938 when Gödel came up with L. And I think this is not his definition, that came later, because he used, to generate the hierarchy, he used just finite list of functions, and kind of a similar list was used later by Jensen. Yeah? So, and that's the list of functions which is suitable for doing inner model theory these days. So, yeah, the point is that the next level, yeah, it's a cumulative hierarchy. So we take unions at limits, but at the next level we just take things which are definable. And yeah, alternatively we could do something a little bit different. We take this, and that would be the closure. Let me just, this root of x is the closure of x together with singleton x under rudimentary functions. And those are the functions. So the point is, these functions are very simple, yeah? And it's a finite list. Yeah. So these are functions everyone kind of uses, and these functions are just to somehow switch the order, because the order triple is kind of not symmetric. Yeah, the definition is not symmetric. These are nested tuples. Okay, and then we can relativize. Yeah, so if we have a set or a class, we can construct the relative to that class. And that's the function 9, which probably should refer to A. Yeah, so there is no A on the left side. Yeah. And in that case, we just keep also closing under this function. Yeah. And that means that at the next level, we just close under all functions, previous functions, and under the intersection with A. And after we go through ordinals, we get the class L of A. And yeah, maybe I should point out it's not adjoining A to L. It's a relative closure, so it may And that was actually in Woodin's talk. If you try to adjoin a super compact measure, you may end up with L. Yeah? So it may happen that L of A is L, even if A is not a subset of L. But, and that's important, if we take a set of, if A is a set of ordinals, then A is inside. So then it is like adjoining. Okay, so that's a well-known definition. And let me list some basic properties of the J hierarchy. Yeah? So we have a uniformly definable partial surjection which maps finite subsets of alpha. Actually, that's a typo also. There should be omega times alpha, yeah? Because ordinals of these are omega times alpha. So there should be omega times alpha there. And it's partial because if we try to do sigma 1 definitions of functions, we cannot, although this one is probably fine, but in general these functions are partial because we cannot guarantee that the domain would be the entire set. I mean, in this case the domain is the entire omega times alpha to be less than alpha, so it will be a total. Yeah. And the definition is uniform, and yeah, that's what I would like to stress because probably not many people are used to this terminology. When I say uniformly definable, that means that I have a single sigma 1 formula, and that formula works. There are no parameters, and that formula works for every alpha. Yeah. So no matter which structure you take, you always use the same formula to define the function, and that's important. Yeah. Also, we have a uniformly definable sigma 1 definable well ordering, yeah, over that structure. Yeah. Again, I have one formula, and that defines the corresponding well ordering over every J alpha. And so B gives us axiom of choice. And then, and I would like to say that right now, because we will return to this later when I try to explain some notions from fine structure. Yeah? So this is a coarse version of fine structure. If you pick any subset of alpha in L, and you look at the hierarchy, that subset appears on the hierarchy, yeah, in some is a member of some element of the hierarchy before you reach the cardinal successor of alpha in L. Yeah? And this is how Gödel proved generalized continuum hypothesis in L. But by localizing this, we get the notion of acceptability, which is one of the central notions in fine structure theory. So we will return to this several times, and I will give several strengthenings of this. So, but it's good to keep in mind that it comes back to Gödel's proof of the generalized continuum hypothesis in L. And then we have a uniformly sigma 1 definable Skolem function, yeah, which goes from omega cross J alpha to J alpha. I have to say something about it. I mean, this term uniformly is a little bit, it depends on something, and that something is what is hidden in this omega. Because what does the Skolem function do? It just, if you give it a sigma 1 formula and an argument, it will return a witness for existential quantifier. So it depends on how we enumerate sigma 1 formulae. Yeah? So at this point I am fixing a recursive enumeration of all sigma 1 formulae. This formula enumerated by members of omega. Those are those are natural numbers, yeah? And from now on, we always refer to that one fixed enumeration, because different enumerations would give you different Skolen functions, of course, yeah? But the important thing is that it's uniform, yeah? So if you take a different J alpha, if you take some J beta, the same formula will define a sigma 1 Skolen function, yeah? And that will be important again. Let me say one more thing, yeah, and that function again, this is a partial function, yeah, genuinely partial function, it's not total, yeah, by diagonal arguments. And then we have a condensation, yeah. So sigma 1 preserving map is just an elementary map where the elementarity applies to sigma 1 formulae. Yeah, and it says that if I have a transitive structure and a sigma 1 preserving map from a transitive structure in some J alpha, then that structure has the form J of some alpha bar. So yeah, if I take an elementary substructure of J alpha and collapse it, we always collapse to the member of the hierarchy. Yeah, so this is what makes it possible to do all kinds of arguments in L. And here are basic properties of the J alpha hierarchy, and it's the same almost. Yeah, just that now I want to point one more thing. Everything relativizes. So let me go a little bit further. So what we have is, yeah, really when I write J A alpha, then I think of it, it's a structure with the domain. So this would be the domain of the structure, and we have a relation, yeah, we have this set A intersection the domain as a predicate. So we really have a language. We need a language with an additional symbol which will denote this set A. Yeah? And we think of it that way. Yeah? It's a language with an additional symbol. So this notation suppresses this, but it's always there. Yeah? So that should be kept in mind. So let me go back. Yeah. Again, there should be omega times alpha. We have a well ordering. We have a global form of choice, but we don't have, of course, GCH in general, because set A can code all kinds of stuff, right? So it can code a large number of subsets of omega, for example. But we will see once we get to extender models. So there are important predicates which will guarantee that D and E will hold. Yeah? And then we have this Skolen function, and let me go to the next slide again. That requires to, if I want to define a sigma 1 Skolen function in the relativized hierarchy, I need a little bit more information about the predicate A. And so this is the first notion from fine structure theory. So this structure is amenable, and that means that that should be X here. Yeah? I'm saying that should say A intersection X is in J alpha whenever X is in J alpha. So I'm sorry, so that's a typo here. So whenever I take a set from J alpha and intersect with A, the outcome will be inside J alpha. So that means that the structure can see small pieces of A, and that's necessary for the definition of the Skolen function. And we will see that amenable structures will play again a central role in what we are going to do in fine structure theory. So let me go back and let me just say something about condensation. It works in a similar way as in L, but we may condense to a different hierarchy constructed relative to a different predicate. Right? So that's the important difference. Again, we will see in the case of extender models, again, it's sometimes true that we condense to the same predicate, which will be relevant in many situations, but not always. Yeah. So let me just say again, that's what I was saying, that when we condense to something else, to a different. Yeah, so we have this symbol, but in the condensed structure, the symbol may be interpreted as a different set, a different predicate. Yeah. So, and okay, so I just listed some basic stuff about L of A, which I assume is well known, but let's just review it. Yeah. So really, what the relative constructibility boils down to just intersecting A with the model. Yeah. So this is what it is. L of A is L of A intersection L of A. And if A is a set of ordinals, then of course I don't need to do any intersection. Okay. Yeah, and then of course there is Gödel-proofed GCH. Jensen did a very fine analysis and proved a lot of combinatorial principles. Yeah. And yeah, so and it turned out that the internal structure of L is too rigid. So L is inconsistent, yeah, with forcing axioms, which are of interest to most of the set theories. And forcing, yeah, and in the end, forcing gives us a much more flexible way of constructing model of set theory. Yeah? So it looks like L, and in a sense, the extender models, yeah, I'm going to talk about behave similarly. Yeah? So the question is, why do we care about L at all? Yeah? Yeah, so even one student once asked me if this is not an entirely marginal thing, this L. So I think to advertise this is that we can often relay the object which we can construct in L, we can relate to V. And by that way obtain some results which do not refer to L, yeah, or that are of more general interest. And that will be the same about extender models. So let me just give one example. So it's a baby example about L, and is the perfect set property. I believe this is due to Gödel. I wanted to check it, but I didn't have time. So yeah, so there is a pi11 set without perfect set property, yeah? And one can construct such a set in L, and the set just picks a code for each countable ordinal. Yeah? So for each countable ordinal, it picks some subset of omega which calls that order type, and one can do this in L in a pi11 way. Yeah? And one can do it also for the relativized hierarchy. Yeah? So say we take X to be a real, yeah? And then we can get a pi11 X set without perfect set property. So what is this good for? Yeah, because long time ago, people tried to prove continuum hypothesis by just proving perfect set property, yeah, and so that's the Cantor-Bendixson theorem, and they did it for closed sets, and yeah, and one can, in descriptive set theory, one can generalize it for analytic sets, which are sigma 1 the same as sigma 1 1, yeah. But so this results tells you that you cannot do it for pi 1, 1 any longer, at least not in ZFC, yeah? Because in L it's false. So that may be of interest, because that tells you that this is not a way of proving continuum hypothesis. But using L you can get more, yeah. So let's just look at what you can do. Yeah, yeah, if you assume that omega 1 of V is a cardinal successor in L of X, or think, so I'm doing more than, I could assume just L, yeah, but this is doing more, then you can just find a real such that which just codes a surjection, yeah, so say omega 1 of V is tau plus inside L of X. So in V you have a surjection from omega on to tau, and then you can find a real which codes the well order of tau. So by adjoining this real to L, you will get a model of the form L of Y whose omega 1 is the same as omega 1 of V. So now using Gödel's theorem and absoluteness, now you can come, the same set he constructed shows you that you have a pi 1, 1 set without perfect set property, but in V now. So just assuming that omega 1 is a cardinal successor in a model of the form L of X, you can construct a coanalytic set in V without the perfect set property. So what's the conclusion? So the conclusion is, okay, so here is it. Here is the picture how it looks. So here is, there are no cardinals, L of X cardinals here, but there may be some tau, omega 1 of V is a cardinal successor of tau. There may be some L of X cardinals here. You all collapse them by adjoining this additional set. And so the conclusion is that if all coanalytic sets have the perfect set property, then omega 1 is a limit cardinal in L of X, and that's true for any X, any real X. So, but omega 1 is regular, so actually omega 1 of V will be inaccessible. So you are using L to prove now a statement where L is not mentioned any longer. If you have perfect set property, then you have a consistency of inaccessible cardinal. And I guess everyone knows that the converse was proved by Solovay. So we are using L to getting large cardinals from some situations, and so we would like to get larger cardinals than inaccessibles, right? So the next step would be measurable cardinals. So let's just briefly recall the definition. You have, so when I say a normal measure, I mean a uniform ultrafilter, has all co-bounded sets. And if I have a regressive function on a measure 1 set, then it's constant on a measure 1 set. And that implies that the measure is kappa complete. So intersection of less than kappa many sets of which are in U is again in U. So this is the next goal, but let's just back up a little bit. So it will take some time to get here. And I want to talk about M ultrafilters. So this is, so the difference is, so if you have a measurable cardinal in some model, then the measure is inside. But this is something, when we build extender models, this is not something we always have. Yeah, what we have, the first thing we usually have is an outer measure. So that's where this comes in. Yeah, so an M ultrafilter is just like an ultrafilter, but it is on this Boolean algebra. So I just take power set of kappa and intersect with M. And the ultrafilter, so the ultrafilter is in V, but not necessarily in M. And when I talk about normality or kappa completeness, what is meant is that it's the function, the relevant functions are taken from M. Yeah, so for normality, that would mean that this function, yeah, and this set would be inside M. Yeah. Yeah. So if I have a regressive function which is in M and its domain is in U, then that function must be constant on a measure one set again. Yeah. You see, because if I fix a value, then the set of all points on which that value is attained is again in M, yeah, because that's definable inside M. And then I have this notion which appeared in literature. When I say countably complete, then that's something different from kappa complete. By that I mean, that refers to V. Yeah? By that I mean that whenever I pick a countable sequence in V of sets such that each of them is in U, then the intersection is non-empty. Okay, yeah. And so and I call that a measure over M. Yeah, and then you can prove all kinds of things. Yeah. So for example, you can prove that if you have such a measure on kappa over M, then kappa is a regular, but it may not have any large cardinal properties now, yeah, because that measure, the model doesn't see the measure. Yeah. Yeah, and then with such a measure, we can do an ultra-power construction. Yeah? So it's just built the same way as the ultra-powers are built, but the functions are taken from that model M. Yeah? So we don't take all functions, we just take the functions from M. And we will see later there is another kind of ultra-powers where we also take some functions which are definable over M in a reasonable way. Yeah? But then you can just do all of these definitions because, yeah, like if you define the equivalence of two functions, because the functions are inside M, the relevant set is inside M, and then you only ask whether the set is inside U. Yeah? So that's a question which is just done not in M, but if you add M as a predicate, it could be decidable in that richer structure. Yeah? So everything goes through, as with usual ultra powers. You can define the membership relation, and this is an important thing. If you have also, if your structure has some predicate on it, then you can define also the predicate of the ultra power. But in general, it is not clear that this set is inside your structure M. So whenever we are going to do that, we only can do it if we can make sure that this set is going to be in M, because now we are going to ask a question whether that set is of measure 1, and this U can only measure sets which are inside M. So once you have predicates on your structure, it's not entirely automatic that you can form an ultra power. Yeah. And this is how I denote, that's how it is denoted, yeah, in literature. So, and we got the Wash theorem, which is formulated exactly the same way, but only for sigma 0 formula. By sigma 0 formula, I mean what is also said bounded formula. So all quantifiers are bounded, no unbounded quantifiers. in general you cannot expect more. Yeah? You wouldn't be able to prove a stronger form of Wash theorem unless you know more about M. Yeah? Yeah? So the formula holds at things represented by the functions if and only if in the original model that thing happens very often. Yeah. Okay, and yeah, so we always form ultrapowers of transitive structures, and we would like the ultrapower to be transitive, and so the crucial question is whether this is well-founded. Yeah. If it is well-founded, I would always consider it transitive. So when I write this, I would really mean the transitive isomorph. And if not, then there is a longest initial segment of ultrapower which is transitive. That's called well-founded power, and I would consider that thing transitive. Yeah. So yeah, so the main challenge here is showing, yeah, okay, so there is the ultrapower map still. Yeah. So the main challenge is showing that the ultrapower is well-founded. But okay, so but before doing that, let's just probably say a little bit more about these maps. The maps, okay, so the Wash theorem holds for sigma 0 formulae, and therefore it's easy to check using this that the ultrapower map is sigma 0 preserving. And it's a general, and also the map is cofinal in the same sense as you wouldn't define it. Yeah, so namely, if I take the pointwise image and take the union, I get the entire range. And such maps, if I know that such map is sigma 0 preserving, is going to be actually sigma 1 preserving. So it's a little bit better. Yeah. And so, for example, if M is a model of ZFC without power set axiom, then the usual proof of elementarity goes through. Yeah. And yeah, we still, I mean, so the usual proof for measurable cardinals, yeah, measurable at kappa, if I form the ultrapower map, the critical point will be kappa. That proof goes through in this setting, yeah, with M ultra filter. Yeah. So the first ordinal moved, the critical point is just the completeness of the ultra filter when measured by functions of the model. Yeah, and then we can also define the measure from the map. Yeah, that's by the reverse process. Yeah, I put those sets into the measure which have the critical point inside their image. Yeah, and we get, and what we get is a normal uniform M ultra filter again. Yeah. And if we start from an arbitrary map between two models, yeah, so now think that we have two transitive models, a sigma 0 preserving map, and we look at the critical point, we derive the measure, form the ultrapower, and then we can just embed this ultrapower into the original model, yeah, just by the element represented by F. We just map that F and apply kappa to it. Yeah, and it's not hard to see that this map is sigma 0 preserving. So, but an important point, because this is how we are always going to prove well-foundedness of ultrapower, by embedding it into a well-founded structure, or in this case into a transitive structure. Yeah, so I can also take M and N to be V, and then we have the conclusion for measurable. Yeah, so. And let me just recall the Scott's theorem that there are no measurable cardinals in L. So, yeah, and that's a consequence of this fact that we have a sentence such that a transitive model satisfies this sentence if and only if it is of the form J alpha. Yeah, so, but that raises a question that, yeah, if we want to do probably if we want to extract large cardinals, a measurable cardinal from some situation, we cannot use L, yeah, because there are inaccessible cardinals in L, but there are no measurables in L. So, okay, so that's the picture. Yeah. That's the Scott's argument. Yeah. So the point is that we shift L to L, and the smallest measurable would be shifted to the smallest measurable, which is bigger. But this argument does not rule an existence of an L ultrafilter. Yeah? So, and it is easy to get one, for example, if we have a measurable. Yeah? If we have a measurable cardinal, then just the intersection of these measurable cardinals with L give us a normal measure over L. Yeah? So remember, yeah, when I said normal measure over L, I meant L ultrafilter, which is normal. Yeah? And here is an important property, and namely, if we have an embedding with critical point kappa, I look at the critical power set of this critical point, which in the sense of M, if we have such an embedding, every subset of kappa which is in M is also in N, because we can map it and intersect with kappa. So that's the picture. If I have a set inside M, we map it using this map, it will stretch the set, but it will not move ordinals below kappa. So this image is inside the target model, and I just shorten it. So from left to right, so in other words, if we are forming an ultrapower, we are not losing subsets of kappa, but we may gain subsets of kappa. So here is an extreme case, and let me just show the picture. Let me just go back. So so H theta is just the usual thing, hereditary cardinality less than theta. So just take a countable elementary substructure and collapse it. And then derive the ultrafilter and take the ultrapower. So so this is I'm just giving this picture because this makes the difference between M ultrafilters and measurable cardinals. Not everything which is true about measurables is true for M ultrafilters. So here I put I of U, but I could have put J. So what happens? This is omega 1. If I form this is omega 1 of this model. If I have an outer measure, it may happen that I have an outer measure, because that's how I get it. I take an elementary substructure of H theta and collapse it. The structure is transitive below omega 1. So the critical point of that structure is going to be omega 1 of that structure. So if I have an outer measure on this, I form an ultrapower, it will shoot this up. So now this thing will be omega 1 of the ultrapower, and it's bigger than omega 1 of the original structure. So this thing is not omega 1 any longer in the ultrapower, it's countable. That means we necessarily added a subset of omega by forming this ultrapower. So these are not very good ultrafilters for our purposes. And so there is this very important definition. So an M ultrafilter is weakly amenable with respect to M if M and the ultrapower of M by U have the same subsets of kappa. So it will not add any new subsets of the critical point. In that case, we say that it is weakly amenable. And I recall the definition. I stated the definition of amenability just for the structure of the form J relative to some predicate, but we can define it in general. Just the structure is amenable if and only if, and now I got it correctly here. The structure can see all small pieces of set A. Now, if you inspect, if you form the ultra power using a weakly amenable measure, and you assume that the ultra power is well founded, if you inspect the thing a little bit, then you are able to prove that from the point of view of the model, this kappa will be inaccessible and evilly weakly compact. But you wouldn't be able to prove its measurability. Yeah. And you get something like amenability. Yeah. So M can see all small pieces of U. Yeah. So by small I mean this X is of cardinality at most the critical point. So yeah, so if, and I forgot to say something here, if I cut M, if I think if kappa is the largest cardinal of M, then this thing would be an amenable structure then. Yeah. But the most important thing is also this. And that tells us that, so this requires a little argument, but that tells us that this set is inside M. Yeah? So weak amenability is actually equivalent to this. Yeah? I have a function on kappa, and then I look at all xi such that the value is inside U, and this set is inside M. Now, if you remember, if we go back and I said when we try to take ultra power of a predicate, then we have to worry about whether this set is inside M, because we want to ask whether it is inside U. So if I put U here, if my A is U and U happens to be a weakly amenable measure over the model, then that's true. So I can actually take the ultra power of the structure together with the predicate. Yeah? So I can take this ultra power, assuming again that it is transitive, it will produce a similar structure. Yeah? Here M prime, and he will give me some U prime, and using the, so it will be sigma 0 elementary and therefore sigma 1 elementary, and a little calculation will, it's easy to check that this thing again will be a weakly amenable measure over this model. So what you can try to do now is you can try to iterate this process. Yeah? Now you take this ultra power and try to continue. Yeah? So then we get, yeah, and I think, so I would like to say something about this because it's a very simple example of iterated ultra power, but all ideas kind of work pretty far, and then with some additional ideas they translate to much higher levels. Yeah? So we will consider such a structure, MU. M is transitive, satisfies a reasonable fragment of ZFC. U is normal measure over M and is weakly amenable. Yeah? And we will often have this. Yeah? M will be a model of ZFC without the power set axiom. Yeah, and this. Yeah, so kappa will be the largest cardinal of M. Yeah, and that means that if we pack any X in M, any set in M, then we have a surjection inside M of the from the critical point onto that set. Yeah, and such a structure, so that's the first approximation to something which would be called a pre-mouse. Yeah, so it would be a coarse one because we don't have any fine structure there. Yeah, but yeah. So a structure of this form, satisfying this, for the temporarily call it the coarse pre-mouse. I mean, later we will have a much more general coarse pre-mouse. Yeah, and also I will use this term in a sloppy way. So sometimes I will use it, I will just say pre-mouse, and it will be either coarse pre-mouse or fine structural pre-mouse, depending on the context, which will, I guess, be clear then. Yeah. Okay, so now we have just one measure, and we try to iterate it. So we iterate it linearly. Yeah. So what does it mean? So my model with index 0 is going to be m. Yeah? And then all other models are determined inductively. Sorry, that's a typo. So at the successor step, we just have our structure mi. So structure mi has this measure ui. So we just form the ultra power, yeah, and the ultra power map. That gives us mi plus 1, yeah, and that determines the measure with index I plus 1. And then we defined all these structures, all these maps, just compositions of these ultra power maps to make everything commute. And at limit steps, we just take direct limits. Yeah? So if I is a limit, then we have a commutative diagram, we take the direct limit and the direct limit maps. And such a thing, yeah, and we call such a thing an iteration if all of these structures are transitive. All mi must be transitive. And when we say putative iterations, then we allow, that would be an iteration of successor length, and we allow the last model be ill-founded. Yeah? That's a technical notion. It's just a convenient terminology for doing proofs. Yeah? And then we say that the structure is kappa iterable if every iteration of length less than kappa can be continued, and iterable if we can iterate it forever. Yeah? So the first observation is, so I would like to now give 3 simple constructions, but these constructions in a straightforward manner generalize to much higher levels. Yeah? But I think it's easier to state them in this case, and it's yeah, so I think it's easier to follow this if you haven't seen that before. Yeah, okay, let me just say, if you think about it, limit steps of uncountable cofinality are not a problem. I mean, if you have an iteration of limit length of uncountable cofinality, then the direct limit is going to be well-founded because ill-foundedness is witnessed by a countable descending sequence, and that countable descending sequence will appear already somewhere earlier. But it's not going to be relevant for these arguments I want to present, but it's probably good. It may give you some feel where the issues are. But probably also I would like to give this picture, at least for those who haven't seen that. So this is how a witness of ill-foundedness looks. So think of this lambda. So say this is a direct limit. So this would be a limit step, yeah, typically. And these are iteration maps. So I try to draw it a little bit that these ordinals actually grow. Yeah. So if you look at it carefully, then they will grow. But so the ordinals themselves may grow, but nevertheless they constitute an infinite descending chain in the direct limit, yeah, because the first one is mapped here, the second one here, and so on. So this way you get an infinite descending chain. Yeah? And this is a useful picture because to keep in mind when you deal with ill-foundedness. Yeah. And yeah, so in particular, if you have a proper class iteration, that's probably one more comment I should make. That's always well-founded. Yeah? So if you are able to iterate through ordinals, at the end you get a well-founded structure. And you see, in the first course in set theory, we are taught that we can transitivize a relation if it is well-founded and set-like. Yeah? So that's an example of something which may not be set-like. So you may not always be able to transitivize it, because simply the ordinals of these things may be longer than the ordinals of V, and I will get to a picture then. Yeah, so this is the first of the lemmata, and that's called the shift lemma. Yeah, so that's the simplest situation. So you think of a situation that you have two such coarse primaries, m bar, u bar, mu, and you have a sigma 0 preserving map of one into the other. And then you form the ultra power this way, ultra power this way, and the lemma says that you can complete this diagram in a way that it makes it commutative, and moreover, this map agrees with this map. You see, they will agree below kappa, because kappa is the critical point of this one, but they will even agree at kappa, so that's the non-trivial part. And that's an important part. Yeah, and that's the map. That's the map sigma prime. Yeah, so whatever is represented by function f, that function is inside this model. You just move the function using the map sigma here and represent, and look at the thing which is represented. Actually, there is a typo. There shouldn't be bar here. There should be u. Yeah. Represent in this ultra power. Yeah. Yeah, so it's this ultra power. So that's the shift lemma. Now, if you iterate the shift lemma, you get the copy construction. And that's a very, very useful construction in a model theory. So what you do, you just repeat that. Yeah. So assume this structure, you have to assume that the structure on the top board is iterable. Yeah. And you have this embedding. So you form the ultra power here, and you just use the shift lemma to do the diagram. Yeah. Then you form the ultra power here. Now, because your structure is up there is iterable, all of these things are going to be well-founded, so you can make them transitive. Yeah? And so you will always be able to complete these diagrams, and you will be embedding the models on the bottom board into these well-founded structures. So they are also well-founded, so you can make them transitive. Right? And what is it going to give you? If the mouse on the top board is lambda iterable, then the mouse on the bottom board is lambda iterable. Yeah? That's a direct corollary, because you just copy, you just take an iteration of length shorter than lambda on the bottom board and you just copy. But it also gives you the following, which I call theorem now. And that's less obvious, yeah. If actually it is good enough if you prove that, if you know that your mouse is countably iterable, then it is lambda iterable for every lambda. So if you can form countable iterations of arbitrary countable length, then you can form iterations of any length. Yeah, yeah? And that's. I don't have a picture for that, but let me just draw the picture for that. So let's say we have this bad iteration where the last model is ill-founded. Yeah, that can be it's inside some big h theta. So we just take this iteration, we take a countable elementary substructure which has this entire diagram as an element, and then we collapse the thing. So here we get some countable iteration of some countable structure which has some countable length lambda bar, but we collapse it, so we have this inverse of the collapsing map, which is sigma. Yeah, but now, yeah, this model was ill-founded, yeah, because this model was ill-founded, and ill-foundedness is absolute. Yeah? Together with this elementary embedding, we had an infinite descending chain, which we just moved here. Yeah? But now we have this sigma here. Now, we are assuming that this structure is countably iterable. So if this was ill-founded, that means that this iteration was of uncountable length. Yeah? But now this iteration is countable, so we can just use the copy procedure to construct a different iteration, possibly. Into which this model is embedded. Yeah? But this is a countable iteration, and we were assuming that M was countable, iterable. Yeah? So this model is well-founded, and therefore this must be well-founded, and that's a contradiction. Yeah? So I'm saying this because this is a typical way how you prove iterability in many situations, not just here, but in bigger models. Yeah? So the point is that you can reflect non-iterability down. Yeah? I mean, here it is not a problem because we deal with linear iterations. The real issue starts when we start dealing with iteration trees. Yeah? I mean, there are these issues with branches do not show up here at all. Yeah? But I think still this is good enough to just to illustrate the basic idea how it works. Yeah? So we just reflect down, but then we just can copy. Down we get an ill-founded iteration which is countable, and then we can copy it, but up there any countable iteration on the top board is well-founded. So there is probably 1 minute, so let me probably say another theorem, and that's the countable completeness. So remember the definition of countable completeness that tells us that if we take countably many, if I take countably many sets, yeah, from the point of view of V, if I take countably many sets from U, the intersection is going to be non-empty. Yeah? So if I have again a pre-mouse, and if I have a countably complete measure, then I can do the following. Whenever I have a countable pre-mouse down here and a sigma 0 preserving map, if I form an ultra power, then I can embed this ultra power back into M. Yeah? In a way which makes this diagram commute. And okay, and I will probably get to this next time. Let me just, I will probably say a little bit more about the proof, but again this construction can be iterated and gives you the proof of iterability. Yeah? If you have a pre-mouse such that U is countably complete, then that pre-mouse is iterable. Yeah? And the proof is the same. Yeah? If you think about it, if you have an iteration on the top board, a putative iteration with the last ill-founded model, similarly as we did here, you just take some elementary substructure inside some big H theta, collapse, you will get a countable putative iteration, but now you can apply this previous lemma and you can embed the first ultra power here, but that gives you again an embedding of a countable pre-mouse into M, so you can take, you can just form the second ultra power and embed it there, and so on. Yeah. At limit stages, this all commute. So at limit stages, there is a obvious way how to embed the limit stages until you get and embed the last one, but that's not possible because that was supposed to be ill-founded. Yeah. So this is how countable completeness gives you iterability. Now, say if you want to construct bigger models, say at the level of wooden cardinals, then countable completeness alone is not going to be very useful, but this picture is still there then. Yeah? So we will get to that. Yeah? So let me probably stop here. I will probably return back to this next time and then continue. Yeah. So thank you for your attention. Yeah. 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 So I should have. Yeah.
More comment? Maybe you want to motivate a bit more this part of iteration because you motivated inner models, but somehow I don't think you motivated why did you want to iterate.
I will get to it next time. Yeah.
Okay.
Yeah. The main. Okay. Yeah. The main thing is that you see we had this condensation thing where when we collapse some elementary substructure of an initial segment of L that collapsed to elementary substructure of an initial segment of L. Yeah? And now you have all of these, now you can have all kind of measures. And we need a tool for comparing them. So these iterations will be a tool for comparing things. And I will give you a specific comparison argument next time. Yeah? So we will get to a canonical primals, and we will show that there is only one such. And that will use this comparison argument. Yeah. So, yeah.
Thanks, Peter, again. This was the last lecture for today. We have a reception at 6 in the lobby.